Welcome to the next lecture in this course, where we will try to see the basics of turbines and pumps. These two are related. The content of the lecture will be, first we will try to understand what is turbo machinery, because there is a field exclusively in mechanical and aerospace, they talk about turbo machinery. So, we will try to see what is turbo machinery, then pumps, what are the different types of pumps. We will try to focus on dynamic pumps, positive pumps, and when we try to talk about turbines, we will try to look at reaction turbine and impulse turbine. Turbo machinery. Turbo machinery describes machine that transfers energy between a rotor and a fluid. It includes turbines and pumps. For example, when you try to extract water from your well, the water is sucked from the well and it is pushed to the overhead tank. So, here a rotor and a fluid interacts with each other. The same way, when we talk about dialysis of pumps, here also what happens is the liquid from one end is sucked inside, wherein which it is purified and it is injected back or pushed back into the body. So, you see that there is an interaction between the machinery and the fluid. While a turbine transfers energy from a fluid to a rotor, a pump transfers from a rotor to a fluid. There is a difference. Friends, understand the difference. There is a transfer between fluid to rotor. When we saw the hydro power corporation and all, what they do is the fluid is used to push the rotor and then the rotor rotates. From there they try to generate energy. So, in pumps, the electricity is given to the pump, it rotates, there is a rotor which rotates, which tries to pressurize the fluid or take the fluid from a lower level to a higher level. It is an important application of fluid mechanics where both turbines and pumps are used. When we try to classify them, they are classified into compressor and pumps. The other one is turbine. They are equally classified. If you see, it is extended, it is enclosed. It is extended, it is enclosed. That means to say it is open, it is closed. So, then under enclosed, you will try to see axial, radial and mixed. Here also, you will try to see axial, radial and mixed. What is axial? Flowing along the axis is axial. When it is flowing along the radius, then it is called as radial, and the third one is mixed of these two is mixed, they have said. So, if you look at the flow, you can see there it flows along. So, here the fluid flow happens along the radius. So, here it is a mixed of both, and choosing this is very important because it tries to dictate the efficiency of the machine. Pumps. Machines that deliver liquid are simply called as pumps, delivery liquid. So, this can be very high flow rate, for example, 100 liters per minute it can be there. From there, it can go to 10 ml per minute. Look at the extent, 100 ml per minute and 10 ml per minute. So, it can go to both in medical applications or in reactor, micro reactor applications, we go this or even less than this. We go to even 1 ml and less than 1 ml for delivery. So, machines that deliver liquid are simply called as pumps. The pump is the oldest fluid energy transfer device which is ever known to us. There are two basic types of pump. One is called as positive displacement pump and dynamic, or it is called as momentum change pump. The dynamic is otherwise called as momentum change pump. Friends, we have seen what is momentum in our previous course. The classification of a pump. So, as I told you, it is positive and it is dynamic. Under positive, we are further classifying it into rotary and reciprocatory. So, this is you have a piston where the piston is moving through a cylinder. So, it is moving through a cylinder. So, this is called as reciprocatory. When it is rotary, you will have a rotor. This rotor is rotated, right, inside a casing. Inside a case. So, that is rotary. Again, in rotary, it is classified as single rotor and multiple rotor. When we talk about dynamic or momentum change pump, it is classified as centrifugal pump or special effect pump. What are dynamic pumps? Dynamic pumps simply add momentum, adds momentum to the fluid by means of fast moving blades or vanes or certain special design. So, here if you see, the discharge comes through this. If you see, this is a plane, it comes through this plane, right. So, there is, when this fellow rotates, that is when impeller rotates, it is going to create something like a vacuum there. So, now what happened? The water is sucked from a or through a pipe on top of this impeller. Now, the impeller rotates. You can see when the impeller rotates, the distance between the impeller and the casing keeps increasing. Okay. So, this one is called as volute. So, in the impeller you will have vanes. These are vanes. The arc like profile which is given, these are called as vanes. So, water enters through this suction, then passes through these vanes, and then it is rotated inside a casing. This casing, the radius increases. So, the momentum increases when it is exiting out. So, that is why it is told as a certain special design. There is no closed volume. The fluid increases momentum while moving through the open passage. This is an open passage and converts its high velocity to a pressure increase by exiting into a diffuser section. So, here in fluid you can do two things. One is you can increase or decrease the pressure. You can increase or decrease the velocity. You can do either increase or decrease the velocity keeping the pressure constant, or keeping the velocity constant, you can do that. And apart from these two, you also have volume which can be increased or decreased. So, these are the three parameters you have. So, within this you try to play a lot. These are significant, by the way. There are other parameters also. So, the dynamic pump can be classified into rotary type and special design. Under rotary, it is always centrifugal. What is centrifugal? You have something which is there, which is rotating at a speed. So, now the media will try to go to the extreme walls, and it is rotating. So, this is called as centrifugal pump, or it is called as radial exit flow. The other one is axial, which we saw. The third one is mixture of both, is mixed flow. When we go to special designs, we see a jet pump or an ejector. Jet pumps are used today in agricultural applications, in farms. Electromagnetic pumps for fluid, for liquid metals are also there today. Then fluid activated gas lift or hydraulic arm are also there. These are all special types which are there, but these are the rotary ones are very common. A centrifugal pump consists of impeller rotating inside a casing. So, this is an impeller. The fluid enters axially through the eye. So, here is the eye. So, this is a drive shaft, enters through the eye of the casing. It is then caught by the impeller blade. This is a impeller and these are all impeller blades. So, caught by the impeller blades and whirled tangentially and radially. So, what is this is tangential and this is radial. So, it is whirled when it rotates, there is a throw of the fluid. So, that goes tangential, whirls tangentially and radially. Radially is when it is rotating like this, the water also goes to the casing, radially outward. The fluid exits through all the circumferential parts of the impeller into the diffuser part of the casing. So, this is the diffuser part of the casing. the impeller blades are typically backward curved, but radial and forward curved designs also exist. So what they say is, they say that this is backward, so backward curved. There can be radial, straight and forward curve design also exist, which can significantly alter the outward pressure. So, through the volute chamber, and when the discharge happens, so here you can try to still play by changing the impeller blade design. So, if you try to plot a graph between the pressure and the flow rate, as the flow rate keeps increasing, you can see here the pressure falls down. So, this image shows how a centrifugal works by displaying its pressure versus flow rate. So, pressure versus flow rate. Flow rate will be always liquid liters per minute. It can be liters, kiloliters, million liters, it can be there. So, when we talk about the usage of STP plants, we talk in million liters, right. When the pump is not moving any fluid, it produces the highest pressure. This is called as the shut-off head here, right, when the flow rate is not there. As the flow rate increases from 0 to 10, the pressure of the pump gradually decreases. This type of performance curve is typically for centrifugal pumps. So, you will see there, as and when the flow rate increases, the pressure drops. Maybe after 10 liter or 20 liter or maybe 100 liter, the pressure almost becomes 0, which is not possible, but it becomes very, very low. The centrifugal pumps are the best for moving fluid at moderate pressures and high flow rates. So, that is why we use these pumps in farms. In agricultural applications, we try to have moderate pressure and we need very high flow rate, because the water has to be sucked from the well and it has to be dispersed, right. They cannot maintain high pressure at high flow. They cannot measure. And for agricultural applications, you don't need the tight requirements. So, friends, this will try to tell you where and when to choose centrifugal pumps. So, it increases the flow rate, the pressure decreases. So, the performance and application, if you see for centrifugal pumps, are generally characterized as high head, low flow machines, meaning they deliver high pressure rise, but relatively at a moderate flow rate. The same thing what they have displayed here. They typically provide a high flow rate and a much steadier discharge compared to positive displacement pumps. Positive displacement pumps are, what are the classifications? We will see that in detail, but here if you see positive displacement, I said reciprocatory. So, what happens when you majority reciprocatory, what will happen is, it reciprocates, it compresses and then it has a vacuum. So, or it has a dull period. So, that is why they say these pumps are much better than the positive displacement pump. However, they are ineffective in handling high viscous liquids. Suppose tomorrow you replace the water with sugar solution, which is used in process industry or in pharma industry or in sauce industry, food industry, then high viscous fluids can be thought of. These fluids, oil, there these centrifugal pumps are not very efficient. High viscosity can lead to a dramatic drop in head and discharge and an increase in power requirement, with efficiency dropping substantially. So, for high viscous fluid, please do not use centrifugal pumps. Axial flow pumps. Axial flow pumps, you can see there the water is flowing along the axis. An axial flow pump is a type of dynamic pump that falls under the rotary classification of the fluid machinery. These pumps are designed to add momentum to the fluid using fast moving blades or vanes. So, there is a diffuser, there is a shaft, right, there is an impeller. So, this is an impeller, this impeller rotates, the impeller rotates. These pumps are designed to add momentum to the fluid using fast moving blades or vanes, converting high velocity into a pressure increase as the fluid exits into the diffuser section. So, high velocity is already there. If you want to further increase the pressure, we use this axial flow pumps. The flow flows almost straight through the pump, passing through fixed and moving blades. These are the blades. Impeller has blades. And nowadays it is pretty interesting. You can have blades as and when you need, you can try to change the orientation of the blade. All blades can be uniformly changed with respect to angle, or you can do only one blade. So, the technology has gone to that level. When you do that, what happens? You try to increase the flow rate and velocity. For gases, we often assume flow is incompressible because the pressure increase is small. Simplified models assume fluid exits blade at an angle and speed related to the blade speed rotation. The Euler turbo machinery formula is used to calculate the theoretical head and power, which we have already seen. In the tutorial, we will have a discussion on it. The ideal head H is calculated using the blade angle and speed, but real performance is usually lower due to the losses. So, now you can clearly see the figure. The schematic figure shows the working of the axial flow pump. The axial pumps are low pressure, high flow machines, opposite to centrifugal pump. Centrifugal pump, what we have is when there is a high pressure, the flow rate is decreased, right. So, here low pressure, high flow machines, opposite to centrifugal is the working style of axial flow pumps. The head drops fast as flow increases. Head is what? Pressure. The head drops fast as the flow increases, meaning the flow is steady even if the pressure changes. The power demand decreases as the head increases. Head is the pressure, head is the overhead, whatever you have. But if flow suddenly drops, the motor overload might happen. And lastly, efficiency is narrow and sharp. So, unlike centrifugal pumps where there is a wide range of efficiency, for axial flow pumps it has a sharp curve. That means to say, if you cross the critical level, the efficiency falls down drastically. So, this is the curve which you see for axial flow pumps. So, pressure versus flow rate is shown here. You can see here there is a drop B between 3 liters per minute and 7 liters per minute. You see the slope falls down drastically, where you can try to see the efficiency. This image shows how axial flow pumps work with pressure and flow. When the pump isn't moving any fluid, zero flow, it creates the highest pressure. It is an idealistic case. Pump cannot be zero and then you can do it. As the amount of fluid flow through the pump increases, the pressure decreases. But there in centrifugal, the fall was gradual. Here the fall is steep. The axial flow pumps are good for moving large amount of fluid, but not for creating very high pressures. So, large amount of fluid if you want to move, then we always go for axial pumps. So, the pump works best when you need to move lot of liquid quickly, but it wouldn't push it very hard. So, here this tried to clearly say where we use this. When there is a flooding situation and where water has to be moved out of the existing space to a nearby space, from a road to a sewage tank. So, then we try to use this axial flow pumps. So, here it will try to move liquid very fast, but it will not be very hard. The pressures will not be very high. That is what we wanted to say. So, the design and application, it can be made in multiple stages to reach a higher pressure. So, why? Because here we try to say large amount of liquid can be moved, the pressure will be low. So, you add one more pump. See, in trains what happens is, when the engine cannot pull all the bogies, they put a double engine. So, almost the same can be made in multi stages. So, it can be one more pump, or you can put multiple stages for increasing pressure. The CFD is used for modern design due to complex 3D flow. Computational fluid dynamics is a software simulation we use to understand the flow and draw it, commonly used when large amount of fluid need to be moved at low pressure. So, for example, in mine ventilation, irrigation, flood control, etc. The free propellers are axial flow device too, but less efficient than the ducted ones. Free propeller, which is their axial flow pump, is used in boats or planes. So, the centrifugal pump and axial flow pump, when we try to plot it against the flow rate and time, you can see here, this is the response we get. The solid line represents the flow rate of the centrifugal pump, whereas the dashed lines represents a axial flow pump. From the graph, it is clearly visible what is the response of individual with respect to time. The centrifugal pump flow is relatively steady and smooth over time. So, that means to say, the sinusoidal, whatever it does, the amplitude is very low. The centrifugal pump is relatively steady and smooth over time. Its output flow has small fluctuations, meaning it delivers a consistent amount of fluid, which is centrifugal pump. You see a large sinusoidal wave. So, this large sinusoidal wave shows that there is a lot of fluctuation with respect to time. So, if you want to have a steady state, what we do is, this pump will be attached to a container where the water is filled and then it is ejected. So, we can try to do that. That is how it happens in water jet cutting machines, because the pressures which is required is very high. So, the water is pushed into an intensifier. So, the intensifier is a tank wherein which it is tried to amplify, and then it finally gives a steady flow out. The axial flow pumps show a huge fluctuation, which is A, right, which very more significantly, which shows that it can go to higher peaks in the flow rate, but it will try to also dip. So, this means to say the flow rate varies more and is less steady. So, you see the magnitude of A, which is very large. The flow rate with a given time, it can go high and low, but in centrifugal pump, it is, though it is sinusoidal, but the magnitude is very low in terms of fluctuations. So, when we get into mixed flow pumps, they are classified under the rotary designs of dynamic pumps. The classification we saw in the beginning. In the mixed flow pump, the fluid passes through the impeller with both an axial flow component and a centrifugal component. This part radial, part axial gives the name which is a mixed flow. So, you can see here, this is it axial flows and then radial flows. To achieve high flow rate, their passages are open more than the purely centrifugal design, which reduces the radial outlet velocity, and consequently the head is produced. Like other dynamic pump, they generally offer high flow rate and steadier discharge. That is why we go for a mixed flow pump. So, here it is, inlet is given through this is the inlet, and then this is an impeller which rotates. Here is a diffuser, so which tries to change the pressure, diffuser, and then it tries to go to a hydraulic motor, and here is an outlet. So, mixed flow pumps are used. The performance and the design consideration for a mixed flow. The mixed flow pumps are designed for application where requires low head and high discharge, addressing the need that centrifugal pump might struggle to display or demonstrate. So, wherever the centrifugal pump fails, then we always look for a mixed flow pump. Their optimum efficiency, like other pump types, is correlated, and their specific speeds and capacity are high. The theoretical understanding of these machines often rely on Euler's turbo machinery formula, which relate power head to fluid velocity component and impeller speed. So, when you look at a pump, what else you will have? You will try to have, one is the motor which rotates, right. So, there is a component called speed. Then there is a fluid which comes inside with a velocity. So, these two are there, right, you see here. Then what you can do is you can try to talk about the power requirement for the motor. So, these are the things which you can talk. So, that is what we try to put, and then in the Euler's turbo machinery formula, we will try to calculate the efficiency, or we try to calculate the pressure, whatever it is, by going around directly or indirectly. Euler turbo machinery formulas will be discussed in the tutorials. The next one is a jet pump. The jet pump works by injecting a primary fluid through a nozzle, which then entrains a secondary fluid in an annular region around the primary jet. So, this is a jet pump, right. So, you see here is a nozzle and here is a throttle you have. This is a diffuser. Okay. So, the diffuser, and here is the return fluid which is there, casing, and this is the tubing which is used in your bore wells. So, there are two fluids, injecting a primary fluid through a nozzle. So, this is a nozzle, right, which then entrains a secondary fluid in an annular region around the primary jet. This process typically involves the Venturi effect. Venturi effect is very common when there is a direction change and when there is a flow change, right. Venturi effect, where the acceleration of the primary fluid in a narrow section creates a low pressure, leading to a suction and entrainment of the secondary fluid. So, primary fluid, secondary fluid. When the acceleration of the primary fluid happens through a narrow section, it creates a low pressure, right. The two fluid streams subsequently become fully mixed downstream. So, two fluids, they mix in the downstream. The resulting mixed flow then typically slows down in the diverging section. Convergent, divergent, we saw that. This is a nozzle where it is converging, then it is diverging. So, when it is diverging, it is called as diffuser. So, diverging section, converting the kinetic energy into a pressure energy, potentially leading to a pressure increase. Jet pump is a complex phenomena, but it finds wider applications today. It has a primary fluid, it has a secondary fluid, right. So, the two fluids subsequently becomes fully mixed at the downstream, which results in a mixed flow. Two fluids mixing flow typically slow down in the divergent section, converts the kinetic energy into a pressure energy. So, these are the applications. You will see lot of this either used in hydraulic packs, or it can be used for agriculture applications, or it can be used in pharma and process companies. The classical application in vacuum suction, for example, by a water jet pump, or in the suction of air fuel mixture into the motor vehicle carburetor, we use the jet pumps. They are used. So, that is why I said, if you read this, the two fluid streams subsequently become fully mixed downstream. Look at the examples. I am talking about vehicle carburetor. Then vacuum suction is also used, for example, in your vacuum pumps which are used in chemistry labs, where you diffuse or where you try to suck all the air in the closed container, we use this vacuum suck. They are used for mixing purpose and to achieve changes in both velocity and pressure within a fluid system. The next one is electromagnetic pump. So, the electromagnetic pump is used to move liquid, a fluid, using the magnetic field, because when you put mechanical, there is a possibility that you can't go higher than a critical speed, one. Second, the mechanical components will have a wear and tear. Third, there is always a weight component which comes in. So, in order to get out of all these things, we try to move into an electromagnetic pumps. These electromagnetic pumps, magnetic field is generated outside and it tries to move the valve which is inside or which is used to even change the direction whatever it is while the fluid is flowing. The electromagnetic pump functions by applying a magnetic field across a conducting fluid. And the other thing is it is used for conducting fluids. What are conducting fluids? For example, if you have a metallic paint, a conducting fluid, or you can try to have iron particles dispersed in a fluid for finishing applications and other things. The movement of the fluid within this magnetic field induces a voltage across two electrodes, right. So, these are electrodes, this is one electrode, this is one electrode. The movement of the fluid which is there, right, within the magnetic field induced by voltage. So, you try to do the very high voltage. So, induced voltage across the two electrodes place in and or near the flow it happens. The mechanism adds momentum to the fluid. So, here the magnetic field is created, right, and here is the voltage which is applied. So, the advantage, the electrodes can be streamlined or integrated into the valve, causing little or no flow resistance. They provide a very strong output for highly conducting fluids. That is what I said, fluid in hydraulic power pack it can be used. Commercially, electromagnetic flow meters are available for most fluid flow, but they are generally relatively costly compared to the normal pumps. The next set of pumps are positive displacement pumps. So, if you go back to our initial slides, it clearly says all these things. So, centrifugal pump, we have finished dynamic, centrifugal, special effect. Now, we are trying to get into positive displacement pumps. Positive displacement pumps, these are shortly called as PDP pumps, are a fundamental type of pumps that operate on a distinctly different principle from dynamic pumps like centrifugal or axial flow type. They are completely different. The PDP pumps works by forcing the fluid through successive volume change. A fluid is pushed through successive volume change. So, this means they trap a specific volume of fluid in a cavity which then opens to admit fluid, right. So, you have a cylinder, there is a hole. So, when this fellow goes and when it comes down, when the piston comes down, so there is a vacuum which is created, the fluid flows inside. This means they trap a specific volume of fluid in a cavity. That means to say you have a container, a bottle, a hole is there. When you move the piston down, the air is pushed inside, the container has a fixed volume. This means that they trap a specific volume of fluid into the cavity, which then opens to admit fluid via an inlet, closes and finally squeezes the fluid out through the output. So, there is a closed volume, you sucked it, now you are pressurizing it. So, there is a pressure which goes. This mechanism results in pulsating or periodic flow, because the piston goes up and down, up and down, up and down as a cavity changes the volume. The positive displacement pumps are one of the two basic pumps with billions in use globally. They are broadly classified into reciprocatory and rotatory. When you look at a positive displacement pump, when you try to put with respect to pressure and you can try to take MPa, pressure and flow capacity, the image shows how a positive displacement pump works. The straight line vertical means that the pump gives the same flow rate almost all time, even if the pressure changes a lot. So, this is what is the positive displacement pump. The curve which is drooping down is the centrifugal pump, which we already discussed. The image shows how a positive displacement pump works. The straight line which is vertical means the pump gives the same flow rate almost all the time, even if the pressure changes a lot. The flow rate is a constant. So, positive displacement pump finds a lot more applications. So, no matter how hard it has to push, the amount of fluid it moves every minute stays nearly the same. This is what makes positive displacement pump special. They deliver at a steady flow. No matter whatever is the pressure, they give a constant flow rate. So, this is a typical example which I gave you with respect to bottle. So, there is a volume which is confined, a piston moves up and down. So, there is flow comes through this, and then you pressurize and then you try to get the outlet. This is for a positive displacement pump reciprocating type. So, the reciprocatory PDP pumps we will see little bit more operate by forcing a fluid along through successive volume change. The working of reciprocatory PDP are discussed in this slide. So, you can see here there is a suction stroke. So, there is a fluid which comes inside, the piston moves back, and then when the piston is compressed, it is moving on the front side. So, this is a piston type. You can also have something called as a plunger type. So, piston is completely arresting the fluid and pressurizing. There can be a plunger type where the fluid is fully filled and the plunger is pushed out. Then the plunger is pushed in, then valve is open on the other side, it can go. You can also have a diaphragm type. Diaphragm type is, this is a hard fixed vertical line, a solid line, the piston end. So, that we can make it little elastic and then we can flow the fluid flow inside and the fluid flow outside. The reciprocatory PDP operate by forcing the fluid along through a successive volume change. The mechanism involves a cavity that opens to admit fluid through an inlet, then closes to trap the specific flow, and finally squeezes the fluid out. So, this is in and this is out. So, you can see for reciprocating pump how are the responses. So, the reciprocatory pumps uses piston moving back and forth to fluid flow like the bicycle pump. So, in the graph, this graph is discussed in the next slide. The pump delivers a steady amount of fluid every minute, no matter how hard it has been pushed, even if the pressure increases. The flow rates stay nearly the same even as the pressure goes up, special feature of reciprocating pump. So, this image, whatever we have shown in the previous slide, shows the reciprocating pump are always pushes out the same amount of liquid, even it has to work against the higher pressure. The rotary pump operates by mechanically trapping a fixed volume of fluid in the cavity and then moving that volume through the pump to the output. So, input, so there is a trapping, then you pressurize and then you exit out. The rotary aspect refers to the motion of the internal component that can create these change in cavities. The principle is almost the same. The cavity opens to admit a fluid, then closes to trap it and finally squeezes the fluid and outlet, resulting in a pulsating or a periodic flow. Friends, keep this mind, the flow rate will be constant for any pressure in both rotary and reciprocatory. The only difference is the pump size or the pump architecture. Okay. So, here is the typical rotary pump. You can see a fluid flowing inside. This is otherwise called as a gear pump. It increases the pressure and there is a flow out. Right. You can also have vane pumps. These are all vane pumps. So, vane pumps are like we have a vane. This is two gears are meshing and then you create. So, in a vane pump what happens? The fluid is flowing inside, there is a vane which is created. There is also a screw pump, right. There is a screw which can rotate, right, like a screw in a nut. So, the intermeshing screw creates a progressive cavity for fluid transfer. So, fluid flows inside, fluid flow outside, this is screw pump. Then you have a lobe. So, here the gear teeth is converted into lobes, trilobes, right. The fluid flows inside, the fluid flow outside. The fluid transfers through the engaged rotating lobes. So, these are the different types of rotary positive displacement pumps. All of them find lot of applications because the flow rate is constant for any given pressure. So, if you plot with respect to the total development head, the pressure which is developed with respect to capacity, you can see the centrifugal pump, the performance falls down, and then you can see there is a rotary pump curve which is a straight line, and then you can see there there is a change in the rotary pump, you can try to have the rotary pump head. This is a change. And then here is a performance variation which can happen because of this change in the rotary. The system pressure head changes when we try to change the performance curve, right. This image shows that the rotary positive pump gives a steady flow. There is a small variation, almost unaffected by the pressure change in the system. So, here is a pressure change in the system. So, here there is a head change, right. A system shown by a nearly straight vertical line. This is exactly how a rotary pump behaves. A constant flow, minimal performance variation of the pressure happens. This is for rotary. Now, let us move into the topic of turbine. Pump, fluid coming and getting it out, right. Turbines are machines fundamentally designed to extract energy when the fluid that possesses a higher head. They are a key part of turbo machinery, a broader category of device that typically connect a rotating shaft and dealing with the fluid energy transfer. It is a bit of misnomer to simply say a turbine is a pump run backward. It's a misnomer. Please don't say that, because its operational principle and design are distinct, although both deals with fluid mechanics and rotary elements. Please don't use this, a pump when it is rotated backward is called as a turbine. No. The turbine are primarily classified into two main categories. One is called as reaction type turbine, the other one is called as impulsive turbine. When you look at the impulsive turbine, there is a impeller which rotates and there are blades. The liquid tries to hit at the blade and then the blade or the bucket. So, here I am calling it as a blade, but in reality it will be a bucket, because blade is a flat one, bucket is something like three-dimensional you have. So, moment the jet of water hits the blade starts rotating. The nozzle are in fixed position. What part rotates is called as the rotor. So, in a moving bucket, this is a bucket. So, there is a fluid which comes and hits the bucket and then it gets out. When it hits the bucket, this bucket is in turn attached to a rotor, the rotor starts rotating. So, here it is called a flow. You can see how does it happen. The fluid which is flowing hitting the bucket and then it is in. So, here these are rotating parts and these are static parts. So, if you drop down the pressure with respect to velocity, you can see how does the water pressure, the steam pressure or the water pressure falls down. Here instead of water you can also inject steam. So, here it can be steam / water injection. So, you can see how the pressure falls down and how the velocity increases, right. This is for a impulsive type. The reaction type, what happens is you will have a rotor. Through the rotor there is a fluid which is flowing and which is exiting out. So, it has a rotating nozzle. So, here it is a fixed nozzle, here it is a rotating nozzle. So, here you can see how the stator looks like and how are the rotating nozzles. So, you see what is the response of stream pressure falling down with respect to the steam velocity increase. The steam velocity you can see how does it increase and the pressure how does it fall down. The reaction turbine is a turbine. The fluid completely fills the blade passage and the energy conversion of head changes. The pressure drop occurs within the impeller itself, right. They are dynamic device engineered to efficiently admit the high energy fluid and extract its momentum. High energy fluid can be a jet of water or it can be steam. The flow through a reaction turbine is generally opposite to that of a pump, with fluid entering at a larger diameter section and discharging through an eye after transferring most of its energy to the impeller. So, what happens is, this is what it is, the shaft is rotating, this rotates. So, you have a blade which is there and then it starts, the water hits and then the rotor starts rotating. So, this alternative blades and graphical illustration continues conversion of both potential energy pressure and kinetic energy velocity into rotational motion. So, you can see here the exit pressure, how does it fall, and you can see here the exit velocity, how does it happen. So, here are fixed blades and here are moving blades, fixed blades, moving blades. So, you see how does the pressure fall down drastically, and the exit velocity is almost the same. The turbine reacts to fluid pressure drop across both blade type, generating forces and making the shaft spin. So, it hits tangentially, so it spins. The steadily falling pressure and cyclic velocity change shown in the image are the key behavior in reaction turbine. So, reaction turbine, this is a reaction turbine. So, Francis turbine is part of reaction turbine. So, here there are radial flow or mixed flow design is there. It was invented or developed in 1849, lending its name to his family of turbines. James Francis did that. So, here if you see here, there is a runner, there is a vane, okay, these are all vanes, okay, and here it rotates. Reaction turbine, we are seeing under reaction turbine, we saw Francis, now we saw Kepler. So, for lower head, a more compact and axial flow design is utilized. So, we use either a fixed or an adjustable blade. So, these are blades where we can fix the profile, in the sense slot angle, with the adjustable blade, providing a greater efficiency at low power setting. So, impulse turbine is what I said earlier. There is a fluid which is flowing from a dam through a penstock. The fluid enters into, and here you have a hand wheel which can try to increase or decrease the length of the sphere. So, the velocity can be controlled. So, the velocity comes and then they hit the bucket which is attached to a rotor. So, this rotates, this is called as runner, this rotates, and when it rotates from here through a shaft, we try to generate electricity. So, this is bucket, this entire thing is under casing. So, the water hits, after it hits, it falls down and it is in the tail race which gets back into the catchment area. So, this is a water jet. So, an impulsive turbine first converts a high head into a high velocity jet through a nozzle. So, through a nozzle, and the jet is allowed to strike the runner bucket. So, and then it passes. The impeller passes are not fully filled. The impeller passages are not fully filled, and the jet flow past the blade is essentially occurs at a constant pressure. So, then the rest falls down and then it goes. So, this is the impulsive turbine. So, as impulsive turbine, we see one example is Pelton wheel. They are ideally suited for high heads. So, the water comes through the penstock and relatively low pressure application. The high pressure is confined to a small nozzle, so which we saw here. Because of the head, the pressure comes through the nozzle, which reduces the need for massive casing thickness in the main turbine. The theoretical power delivered is proportional to the fluid mass flow rate, the velocity, the function of the jet velocity and the bucket speed. Okay. So, this in turn you try to drive it out. The maximum power is achieved when the bucket linear velocity is approximately half the jet velocity and the bucket velocity. The nozzle losses are accounted for by a velocity coefficient typically 0.92 to 0.98, while efficient impulse turbines are generally not quite as efficient as Francis and propeller turbine, as their efficiency are very high. So, this is how a Pelton turbine looks like. To recap, in this lecture we saw what are turbo machineries, what are pumps, their classifications, what is a dynamic pump, what is a positive pump, what are turbines, different types of turbines, that is reaction turbine, impulse turbine, we saw that. This is a very important topic, because when you see any electrical system, you will see there is a pump or there will be a motor. So, you will now onwards start appreciating how does these pumps and motors work and how are they making our life easy. If you try to take an AC unit, you will have a compressor, again there will be a motor. If you try to see a mixie which is there, there will be a motor. Right? So, there is a motor, this motor will be attached to a pump. So, this pump is used for various applications. When you take a desert cooler, there is a pump which is used to suck water and then take the water to the higher heights, altitudes. From there it is dispersed to the sawdust or any other media, and when the air is blown you get a cool feeling. So, there also we try to use pumps. You get pumps from 100 rupees to few crore rupees. So, that is the variation depending upon the requirement you decide. These are the references which we have used, friends, and thank you very much.